Good morning all. Welcome back to the class. Yesterday we talked about the quick sort design to a lesser extent, and we talked of having analysis done for the corresponding quick sort recurrence relation, and then we have also seen the basic cases, worst case, the best case, average case. So let's resume the discussions, and to start with quick sort, we have already discussed some of the common related points about its salient programming related features and analysis. And now we understand that whenever we have a recurrence relation, we have probably to think of the characteristics in case of a best case, in case of a worst case, in case of an average case. In some cases, like merge sort, all cases are same because data characteristics won't affect the size of individual sublists. But in case of algorithms like quick sort, the cases are different and the total time complexity can differ. So today we are going to talk about various notations. Like we have been using big O notation. We also talked the last time of a theta notation, but there are some more also. So we are going to talk of various asymptotic notations which will be used for the analysis part in a big way, and how they are different from each other. That is what is the focus for today's class. So we are going to talk about those usage. But before I go, let me just quickly revise and have certain special features about the quick sort which you did last time. One important point which I could not focus upon yesterday, let me just share. I am sure if you have implemented while doing quick sort analysis, etc., what we have already said that we are going to design and do some coding like this. But during coding, the point which we need to really take care is that whenever we talked of having the pivot element to come at this position, first thing is word pivot will be probably incorrect here. To be precise, the pivot element coming here doesn't mean pivot variable to be stored. Ideally, I should have here array ent, not pivot. Why array ent? Because pivot is a separate memory variable within which you got your pivot value stored. For example, if we have used pivot as, let's say, 18, so then 18 is supposed to brought here, but pivot as a separate variable has 18, and 18 in the array is actually at end index, not just the pivot variable. So this value from here should reach to the corresponding place. Why I am saying this? Ultimately, we have to swap ARRI plus 1 or whatever was that location. These values are to be swapped. So swapping with a pivot will not work. You have to do the swapping with ARR index. Indirectly, that meaning that pivot reaches to that position, but whatever was the actual value at that in I plus 1 or whatever index, that should not be lost. So we are going to actually do the swapping. I'm sure while implementing, you might have seen this and done correctly, but if you have not done, I just wanted to share with you. And just before that we continue further, let me just quickly show you some of the sample code as a working code of the Corman's quicksort version. So that will make the things more easier for you. And let me just show you Quickman's complete version of this. So Corman's version I have shown last time, the prototype, the sample code, the fill in the blank kind of a code. But now I can easily see that what will be the total code. So of course, I have got the proper indentation done as we corrected last time. And then I said, yes, this is how I will be calling. If I want to verify, then I can print the pivot location to confirm that whether I'm getting correct or not, otherwise not needed. In the partition, we have done everything which we discussed last time, that yes, how many times we have to repeat. We can see condition, what should be there. We can see swapping with I++ position, etc., or interchange of that value with the temp I, array I versus array J will be needed. Here also, now this is what I was stressing upon, that when you said that ultimately you have to bring value of pivot to the correct position. So effectively here I am going to have array I+1 with array pivot or pivot index to be swapped. So if I have here the variable pivot taken as a pivot index, so I said that pivot index is n. Then every time I compared the value with ARR pivot, and then finally ARR pivot being swapped with ARR I+1. So this is how my implementation will be there. Of course, those who are better programmer, instead of looking at this code, they should try to do of their own. But those who are not able to do programming at present, for them this will be a good useful code to practice. That's it. Now let me resume from the asymptotic notation discussions, and let's resume back from here, and let's continue to the discussion related to asymptotic notations. So let me just enable my file pointer. Yeah, pen is ready. So now I say asymptotic notations. Asymptotic, mathematically you have studied this work. So in maths you have studied, and effectively you know what asymptote means. So effectively, if you are having some value going towards, say, in a longer run, going towards infinity or towards a particular value going to touch upon that, this is what kind of asymptotic means. So effectively, we say for large values, for towards large values, and what will be the approaching limit, effectively, we are going to see that. Approaching limit or the boundaries or thresholds or approaching limits is what we are targeting to find through these asymptotic notations. So, of course, this is not a very precise way of estimation, but yes, this is one of the acceptable way of estimation. Well, you have been using big O notation. We normally call it as a big O or big O or whatever you speak. But last time we also talked of a theta notation. Along with that, there are some more, but we will understand it through an example, and we will initially understand and formally define the theta notation first. Once we define theta notation, then other defined definitions will become easy. So we will formally define the theta notation. Through that, we will be able to define big O notation also and other notations also without much difficulty. For example, let's assume there is some algo 1 I call, and algo 1 has a step count to be found as n square by 2 minus, let's say, 3n, maybe something more also. So n square by 2 minus 3n is what I have found step count using some analysis, etc., various loops, etc., all studied, and I find that this is going to be total number of steps taken by this. What is its time complexity in the big O notation? So now we will understand that first and then define it formally. Time complexity in theta notation, I can say that algo 1 has time complexity as a theta n square that will effectively mean, it will mean that there will exist some constant. If I say theta n square is its time complexity, that theta will mean there exists constants, positive constants, I'll say positive constants, C1, C2, and n naught, such that Effectively, Algo 1 step count is sandwiched between, it's a sandwiched between C1n square and C2n square for all n greater than equal to n naught. N square coming from where? N square is the same as this n square at both places. What does that mean? I mean that I should be able to guaranteedly find some value for C1 such that n square by 2 minus 3n is sandwiched between C1n square and C2n square. This is what must be true for all n greater than equal to n naught. If guaranteedly I am able to find C1 and C2 to satisfy this mathematical relation for larger values of n, if it is satisfied, then I say my time complexity of this algo is claimed as theta n square. So if I say that yes, I have n square by 2 minus 3n and I want to satisfy whether I can get C1 and C2 accordingly or not. So accordingly, I can say it will be equivalent to saying C1n less than equal to n by 2 minus 3 less than equal to C2n. And then if you solve it, you will be able to get a C1 equal to something, some positive value, C2 equal to something. If you are able to get that, this is precisely what a theta notation means. Loosely speaking, we already said that n square by 2 minus 3n is said to have time complexity of saying a big O of n square, or I said even theta of n square, because rate or growth of the time, growth of this function depends on n square actually. I can easily see that. So dominating term is n square out of this whole mathematical relation. Dominating term was n square. So that was a loosely speaking, and dominating term is actually n square. But that was what we said loosely. Now mathematically we will define formally the same thing. So I now, knowing this definition, I will give it as a total definition. I will say consider some function fn which tells the step count of algorithms, some algo. For example, we have taken n square by 2 minus 3n. I say consider fn, it has time complexity theta of gn. For example, for me, gn here is n square. So remember that. So I say it has got complexity theta of gn if and only if there exists C1, C2 and n naught such that C1 into g of n is less than equal to f of n less than equal to C2 into g of n for all n greater than equal to n naught. N naught. What does that mean actually is that if you are plotting this for a large value of n, then what we will say is if the some function fn is growing like this, then I will have something like this as C2 of Gn, and maybe anything like this as C1 of Gn, and this is my Fn. So effectively, Fn is sandwiched between these two curves. Sandwiched will mean I have an exact bound. Why? I say Gn remaining same means if I am saying n square complexity, then with a constant it will become always that Fn will be having a greater than or equal to C1 n square, but another constant will exist with the same dominating term and Fn will be less than to equal to this for some larger values. Initially it may get violated, but n naught will be this. From this point onwards, it is guaranteed that Fn is less than equal to C2 into Gn, and Fn is guaranteedly greater than equal to C1 into Gn, and this side it is less than equal to. So I can easily see that this is greater than equal to, and this is, so this is my Fn, and my Fn will always behave from this point onwards. It will be always greater than. Yes, so the power connection was cut in between, so there could be a glitch in between. Now I am resuming. So we were talking of that whenever we have some curve which is, let me just have the pen. Yeah, so this is my total count. So I say it is a sandwiched, and in between same equations sandwiched for Gn using two constants. Same constant, same Gn using two different constants. So if it is so, then I say I'm able to find the exact bound notation using two different constants. What is the crux behind this? Effectively, what we have said is that we are able to find, I'll say we are able to find some Gn which becomes a lower bound as well as upper bound. So that is the advantage of this. If so, it is called as a theta notation, or it is called as an exact bound. So theta is best notation because this will give you an exact estimation, neither lower nor upper. On the other hand, big O, when you said big O notation, big O or big O, whatever you say, is actually nothing but it's an upper bound. So it is again a asymptotic notation, but it says Fn has time complexity O of Gn if and only if there exists some constant, there exists some constant, let's say C and n naught, say you could say C1 and n naught. such that I'll take it as a C2 and N node such that Fn is less than or equal to C2 into Gn for all n greater than equal to N naught. So this is upper bound that Fn is O of n is upper bound. Fn will be always less than or equal to this. On is either equal or it will be greater than step count for large values of n, and dominating term will be guaranteedly known to us. So this is what it means. Effectively, this it means is, well, if I have Fn to grow like this, then I say big O of n means start from anywhere, but ultimately this is O of Gn. So Fn will never overshoot this. Fl will never go beyond this for large values of n. So there could be somewhere n naught. Beyond that, it will never go. And when I continue with the same notation discussion, then I have another omega notation. So omega notation, it means nothing but actually it's a lower bound. So lower bound meant that I will say Fn has time complexity omega of Gn if there exists some constants C1 and N naught such that C1 into Gn less than equal to Fn for all n greater than equal to n naught. It means Gn is the lower bound. So minimum this much time complexity dominating term is guaranteed, and Gn means effectively if I have estimated something or if I am able to find that as a lower bound, this is what omega notation means. So this is called as omega. Some of you might be aware, some of you might not have heard this earlier. So effectively, if I have drawn somewhere as this is Fn, then mathematically or symbolically you could say this is C1 into Gn. So this is what I'll say C1 star Gn, whatever you say. So this is a lower bound. So now you can easily appreciate that we defined initially theta notation. Theta notation helped me to find out an exact bound. And through this, we can also define upper bound using big O and lower bound using omega. Exact because same Gn is bounding it in both sides using different constants. In both sides using different constants. So that is it. That is why I said same. So if the Gn is the same, I can guaranteedly claim. Let's take certain examples. So if I have, let's say, some equation 3n plus 5n minus 6, say these are the total steps effectively equivalent to saying at 8n minus 6. Then I will say, if I have to estimate its a time complexity, guaranteedly I will say this will be said to be something like as a theta of n, because maybe something like if I say 10n, or I'll say I'll put let's say as 7n, probably less than equal to 8n minus 6 and maybe less than equal to 10n for all n greater than equal to something, let's say 5. For bigger values of n, I should be able to have this relationship true for every possible value of n. If I am able to have something like this, then I can say I am able to estimate correctly. So say I am able to find C1 as like this, C2 as like this, something approximately I can say I can easily get something like this done. Of course, exact value you can find out. Similarly, even if I had the value to be, let's say 3n plus 25, still I can say 3n plus 25, still I will be able to say that this has got a theta of n, because I will be able to say something as here, let's say maybe I could say 4n, say 4n less than equal to 3n plus 25, and maybe I could say less than equal to 5n, something like this, or I could say I will be able to have this relationship established for all n greater than equal to, let's say 10, something like this. For 10 it will be 30 plus, or maybe not 10, maybe I could say for 20, let's say. For 20 it will mean 20 into 3, 60 plus 85. So maybe you could say something like this. Or even if you could say I have, let's say instead of for 20 I could find out say for 22. So for 22 I could easily say by 22 into 23, 66 plus 25, or I'll say something like this will come. Maybe I can say 23 3 or 23 into 4. So for something allowed for our n greater than equal to 24, I can easily say that I will be able to have something like this. So maybe I can say I will have here instead of a 4 something else taken, maybe I can say 3n, and then this side I can have even 4n, and then accordingly also I can have. Let's say similarly I have an equation, say 6n square minus 5n plus 8. Now 6n square minus 5n plus 8, I will be able to guaranteedly say that some C1n square less than equal to this will be possible to find mathematically by writing some C2n square for all n, let's say greater than equal to, let's say 10, something like that. Maybe I will say C1 could have been, let's say 5, and C2 could have been, let's say 7, something like this, and then accordingly I'll be able to find all that. So this is what exactly will mean, this will mean theta of n square. On the other hand, big O means that I am just trying to see on the other side. So big O effectively still will mean that I can definitely write 6n square minus 6n plus 10 to be less than equal to, let's say 8n square for certain n greater than equal to this. For larger values of n, it must satisfy everyone. For some initial values, even if it doesn't satisfy, no, it's not a big issue, because n is normally assumed to be very large. So that will straight away mean big O of n square. This is what exactly asymptotic notations mean. So I will be able to use this and do that. Now, even if I say that I estimate it wrongly, O of n cube will also be correct, because still it will be possible to write it as 6n square minus 6n plus 10. Maybe I am able to write it as less than equal to 5n cube for some n greater than equal to, let's say 3, or greater than something like this, say. So n cube might satisfy this. In that case, I can claim big O to be n cube, but theta of n cube will be incorrect. So big O of n cube can be okay for this, but the theta of n cube will be incorrect, because 6n square minus 6n plus 10, if this was the step count for some algorithm, it will be impossible to find out something here constant C1 which will satisfy 6n square minus 6n plus 10 for large values of 1. It will be not possible at all. Hence, I will say theta of n cube was impossible. This is not a theta of n cube, it is incorrect. Because theta n cube wanted this side also to be satisfied and it wanted this side also to be satisfied. So this side might get satisfied, may be okay, but other side may not be okay at all. So this side will be not possible. Similarly, if I am saying 6n square minus 6n plus 10, it can be said to be having omega of n square. Okay. Even I can say omega of n also to be okay, because I will be able to write some C1 into n to be satisfying this for large values of n. Yes, possible. I can have this. But theta of n will be incorrect, because theta of n means I should be able to satisfy it from both sides. Now, this side still possible, but this side will be impossible. So, if I claim this to have a theta of n, it will be incorrect. So, theta is definitely a better notation to use than other notations, because it will give me a tight bound. On the other hand, big O and omega gave me not to have tightness also. Then comes two more notations. One is called as a small o and other is called as a small omega. W symbol is effectively what small omega means. So small o means more than tight. Definitely upper only. Tight will be relaxed. Means my Fn should be less than C2 into Gn. Then I will say it has O of Gn. Like if I say n square minus 3n, 6n square minus 3n plus 8, I can guaranteedly say this to be C2 into n cube. So big O notation said it n square or n cube, but the small o notation will say it has to be estimated more than equality. No equal symbol is used here. So big O is upper bound, but with the tight also allowed. Small o is more than tight, that is upper bound only, not equality. Similarly, I can say when I say small omega, so small omega means not tight but lower bound. So lower bound but not tight means equality will not be still there, meaning that my omega of Gn will be possible as a correct answer if and only if I am able to have C1 into Gn to be less than Fn. For example, if I say 3n square minus 6n plus, let's say 8, I can guaranteedly say I can write something as C1n, or even I can write C1n log n, because for bigger values of this, equality will not come into picture. No equality. So small omega and small o notations are rarely used because there is no use to over or underestimate. So small o means overestimation and small omega means underestimation. So obviously not a good solution at all. So normally theta is very commonly used, big O is also used, and omega also sometimes will be referred. Then there is a theorem given in the book, theorem 10 point, let me just see the number, 3.10. So you must read from the book the theorem 3.10 and revise that and make conceptual and theoretical understanding also sound about this in various discussions, especially in the interviews when asymptotic notations are discussed. Not only your clarity of finding asymptotic notation will be asked, but they will also would like to see how clear you mathematically understand these notations. So read from the book, and if any confusions, you can definitely ask me anytime during the class or maybe after the class in my room also. With this, we are going to wind up. And before I wind up, let me say that now the next classes, next 2 classes or next 2 to 3 classes, what we are supposed to cover is the how to estimate the time complexity for recurrence relations. Because for non-recurrence, now you can easily know, you can calculate time complexity of any step count using these symbols, theta, big O, etc. But for recurrence relations, there will be different mechanisms to measure that. One method is called as a substitution method, which is not a very good method, but it's an intuition-based and guess-based method. Second method, which is used very frequently, is called as a recurrence tree method. So this will be systematically developing a tree and then expanding a tree for its substitution with the corresponding new parameters or reduced n size, and then expanding it further and then finally finding out the total time complexity. And third method, which is called as a direct shortcut methods, that is called as a master theorem. Very important theorem. In all algorithmic discussions or any interviews, you can expect some question on the master theorem, which has the 3 cases. And we are going to see that using those 3 cases, you can directly compute without any more mathematics needed. You can directly find the time complexity of any recurrence relation. Using that theorem, using those 3 rules, you can directly find. So our next 2 to 3 classes will focus on this. Subsequently, we are going to focus more on then we are going to back to various algos design and analysis. So lot of programming will come, and then of course design will also mean analysis at all times, but we are going to see various new algorithms will be designed time to time. Bye-bye, all the best. Best of luck to you. Let me just save this and stop sharing, stop recording.